Perhaps the easiest example of a simple harmonic oscillation is a spring with an object at the end. Let's suppose we have such a spring here. This would be the spring in relaxed position. I call this x equals 0. And I arbitrarily call this the plus direction and this the minus direction. So this is the relaxed spring. And I extend the spring with an object mass m here. And this position equals x. The spring, in my approximation, is massless. There are no massless strings, but what it means is that the mass of the spring can be neglected compared to the mass of this object. Also, there is no friction of any kind. This could be on a horizontal table, a frictionless table, and there is no air drag. It's an idealized situation. The spring has a spring constant k, and when I bring this object out over a distance x, there is a restoring force, the spring force that is driving it back, F to equilibrium. F, which is that force, according to Newton's law, equals ma. A is the second derivative of x versus time, so I can write m times d2 x dt squared, but I prefer to write for the second derivative an x with a double dot, and for the first derivative an x with a dot. So I get m x double dot. Now the magnitude of x equals kx, if it is an ideal spring, if Hooke's law holds. But f is a vector. It has a magnitude and a direction. And since this is a one-dimensional problem, I can simply remove the vectorial notation and simply write f equals minus kx. Notice that when x is positive, automatically f will be in this direction, will be negative. And when x is negative, it's on this direction, notice that automatically the force will be in this direction and will be positive. So this minus sign takes into account the fact that f is a vector. The minus sign indicates that there is a restoring force. If x is positive, it wants to bring it back to equilibrium. If f is negative, it wants to bring it back to equilibrium. So I can now rewrite, forgive me for my cold, so I can now rewrite f equals m x double dot simply as minus kx equals m x double dot. I get mx double dot plus kx equals 0. I divide by m, and I get the famous relation x double dot plus k divided by m times x equals 0. And that is famous in that this means immediately when you see this, this is a simple harmonic oscillation. K over m is a given for a particular system. Let's write in more general terms for it C. So we write for this C for now. So I could have then a differential equation plus C. X is 0, that would be a simple harmonic oscillation in X. If you ever encounter something like this, the C's could be different of course, then it would be a simple harmonic oscillation in Y. And if you ever encounter something like this, then it would be a simple harmonic oscillation in terms of an angle, like we had with the pendulum, the angle theta. The solution to this equation, any one of these equations, the solution is that x equals a times the cosine of omega t plus alpha. You may prefer a sine. If I choose that, then x dot, which is the velocity, would become minus a times omega times the sine omega t plus alpha. And that means x double dot would become minus a omega squared times the cosine omega t plus alpha, and that is the same as minus omega squared times x, because you see x a cosine omega t plus alpha here, and so this is x again. And I will substitute this result now in this equation. I'll call this equation number 1. So I have to substitute x double dot, and then I have plus cx. What is x double dot? That is minus omega square x plus cx equals 0. I don't think we need this equation anymore. It's clear what I have done. X double dot is this value, and cx is this value. So I leave this on the floor for now. This is 0. And so you'll find immediately that this is true and only true if omega square equals c, and so if omega equals the square root of c. And so in the case of our spring system, omega, the angular frequency, would be the square root of k over m in radians per second, and the period of the oscillation in seconds, which is 2 pi divided by omega, would be 2 pi times the square root of m over k. And this will then be in second. Omega, which is the angular frequency, equals 2 pi divided by p. Now notice that both omega and p are independent of a and independent of alpha. A and alpha depend on the initial conditions. For instance, this is only one example. If you chose the time t equals 0, and you're always free to choose what you call time t equals 0, if you choose that at the moment that the object x is at plus a, and that the velocity at that moment equals 0, then you will find, and you can convince yourself of that, that alpha equals 0 when you have this cosine term. A then is the amplitude of the oscillation. It's the maximum displacement in one direction, and then it is the maximum displacement in the other direction. But this is, alpha is only 0 if you define it in this manner. If you define the time 0 at other moments of time, then alpha will not be 0. There is not that much physics in alpha. Really all the physics is in the omega and is in the period.